This presentation deals with measuring the electromagnetic properties of materials using transmission line techniques. The transmission line could be an air line, section of waveguide, or two antennas pointed at each other with the sample placed between the two. The electromagnetic properties are permeability, permittivity, and conductivity. The electromagnetic properties appear in Maxwell's equations. In Maxwell's equations, J is the current density, E is the electric field intensity, D is the electric flux density, H is magnetic intensity field, B is magnetic flux density, and P is the charge density. These equations are always satisfied. Most materials are non-magnetic. For non-magnetic materials, the permeability is equal to that of free space and essentially constant. Its units are henries per meter. Conductivity is the degree to which a material conducts electricity. It is one of the properties that varies the most widely. It can be separated into three general categories: conductive materials, semiconductor materials, and insulators. Permittivity describes the interaction of material in the presence of an electric field. It's a complex number and is normally normalized to the permittivity of free space. The real part is a measure of how much energy is stored in the material. The imaginary part, how much is lost. If you look at the second term that has to do with conductivity and the frequency in the imaginary part, note that as W gets larger or much larger than the conductivity, that term goes to zero. Sometimes permittivity is referred to as dielectric constant, even though it is seldom constant and normally varies both with frequency and with temperature. Loss tangent can be calculated from permittivity. It is the ratio of the imaginary part to the real part. So very low loss materials will have a very low loss tangent. Higher loss materials will have much higher loss tangents. There are several mechanisms that causes a material to have a particular permittivity. One such mechanism would be if the molecules in the material can rotate when electric field is applied. Another case, when the electric field is applied, it causes a stretching of the molecules in the material. And then a third would be where the individual atoms in the material are stretched. Anyone involved in the design of semiconductor components, electrical circuit board, or individual discrete components would have an interest in knowing the permittivity of the items that they're designing it with. More recently, people that are designing low observable vehicles, stealth vehicles, would have an interest in knowing the permittivity of the material. Permittivity, or dielectric constant, has been shown to be an indication of other physical properties of materials. Two I'd like to point out would be moisture content. The moisture content of cereal grains can be measured in almost real time, as opposed to using the traditional techniques of weighing the material, drying the material, and then weighing again, and then calculating the moisture content. This typically takes over 24 hours. Another area that shows a lot of promise is in cancer detection. Healthy tissue has a different permittivity than cancerous tissue. So this has been shown to be very helpful in the removal of breast cancer cells and determining whether all the cancerous material has been removed. There are several techniques that can be used to measure the electromagnetic properties of materials. Starting up at the top on the left-hand side, parallel plate capacitors can be used primarily to determine the permittivity of material. On the right side, coaxial and waveguide probes can be used to measure it. It's very useful for liquids in the case of the coaxial probe, and in the case of the waveguide probe, measuring lossy materials such as concrete. Been a lot of research in this area. If you're measuring very low loss material, and this is very important to you, then using some type of resonant cavity technique would be of interest. We will not be covering these in this presentation, and we may cover it in future presentations. We will be concentrating on the transmission line techniques. Here, the transmission line could be an air line, a section of waveguide, or two antennas with a sample placed between the two antennas. Each of these techniques has different uses over different frequency ranges, which we will investigate. A vector network analyzer is used to make measurements on airlines, waveguide, or free space sample holders in order to determine the electromagnetic properties of the material sample placed in them. A vector network analyzer measures S parameters. S parameters are ratios of incident and reflected or incident and transmitted electromagnetic fields under the condition that the source is a Z0 or matched load, and the load on the end is also a matched load. The most common sample holders used for these measurements are coaxial, waveguide, and free space. A coaxial sample holder is an airline. To make the measurement, the material is machined so it fits between the inner and outer conductors of the airline. Once this is done, it can be connected to the network analyzer and S parameter measurements can be made. A waveguide sample holder is simply a section of waveguide. To make the measurement, the material is machined so it fits snugly inside of the waveguide. The limitation on this technique is the frequency band of the waveguide. Shown here is a W-band system, free space. It consists of two corrugated antennas. These antennas are directed towards mirrors, which reflects and focuses the beam towards the sample holder. In this case, the sample is the white piece of material between the two mirrors. This type of system has been implemented anywhere from 12 gigahertz up to 1 terahertz. This is probably the most precise free space fixture for this type of measurement over these frequency ranges. When the sample holder is connected to the network analyzer, the measurements that can be made would be the reflection off of the sample and the transmission through the sample. In doing the calculations, which we'll discuss later, there are several assumptions that are made. These are shown on this slide. Once the S parameters on the sample holder are measured, we need some way of calculating the material properties from these parameters. The equations shown are for TEM waves, which will be assumed for both coaxial and for the free space measurements. In the case of waveguide, the equations are slightly different where the cutoff frequency of the waveguide band comes into play. Once we have the S parameters, we need to calculate the material properties. There are several techniques for doing this. Generally, they're referred to as models. Now, these models fall into two different categories, one that are for magnetic materials and the other for non-magnetic materials. We will take a look at each of these individually and talk about the advantages and disadvantages. Nicholson-Ross is probably the most famous way of doing this. Nicholson-Ross back in the 70s found that if they took the sum and the difference of the reflection and transmission, they could algebraically solve for the material properties as a function of frequency. There are a few considerations you need to take into account when using the Nicholson-Ross model. Anytime that the reflection off of the material is equal to zero or close to zero, you end up with one equation and two unknowns, so it becomes inherently unstable. Another problem is that the derivation involves taking the log of a complex number. The log of the complex number is not a single valued function, so you need some way of determining which of those log values you need to use. This shows the problem where S11 approaches zero during the measurement. On the left-hand side is a measurement that gives us the approximate values we would expect for a measurement on Teflon. On the right-hand side, we see two glitches at different frequencies. This is caused when the reflection off the back of the sample cancels out the reflection off the front of the sample, and the system becomes unstable. We will see later that if this happens, there's basically two choices. One would be to use a shorter sample. The other would be to possibly use a different model, and maybe you only use Nicholson-Ross to identify this material as non-magnetic. Fortunately, Nicholson-Ross should probably be used for the most part for measuring magnetic materials, and magnetic materials, this situation seldom happens. Shown are measurements of magnetic material using Nicholson-Ross. The polynomial model assumes that the material properties, either the electric or magnetic properties, can be approximated by a polynomial. In the equation shown, y is the complex material property and x is the frequency. This differs from some of the other models that we've discussed so far in the fact that it basically solves for the entire frequency range at one time. Rather than use the normal representation of a polynomial, the various coefficients times the various powers of the independent variable, we are using the Lagrange representation of a polynomial. This is based on order pairs, where for various values of y, we know the value of x. Here are the steps that were used in order to determine the polynomial that represents the various material properties. We'll first assume a zero-order polynomial, a constant. We'll adjust the y of n's for the best fit to that polynomial for both S11 and S21. After we're finished getting the best fit, we calculate the average difference between the measured and the calculated parameters. If the average fit is larger than the expected errors, we'll increase the order of polynomial and repeat the process described. When we're finished, we can calculate the permittivity over the frequency range by using the polynomial. The measurement shown illustrates in the red the polynomial fit, and in the blue the fit using the Nicholson-Ross model. As you can see, because of the technique of measuring or calculating the appropriate values over the entire frequency range, we get much better and we avoid the glitch when S11 approaches zero. This measurement shows the measurement of magnetic material using both the Nicholson-Ross and the polynomial model. As you can see, the polynomial model seems to tolerate or is less affected by measurement error and measurement noise. The NIST model was developed by scientists at NIST in Boulder, Colorado. This technique uses all four S parameters to calculate permittivity. It assumes the material is non-magnetic. The fact that they use all four S parameters eliminates the need to know the position of the sample in the sample holder. It sometimes has a problem when the errors in the reflection measurements are large. This is a measurement of Teflon using the NIST model. As you can see, you get pretty much the expected result. The transmission model only uses the transmission coefficient, S12 or S21. This technique is iterative. It minimizes the difference between the measured and the calculated value of the transmission coefficient at each measurement frequency. Much like the NIST model, the sample is assumed to be non-magnetic. It often converges when the NIST model fails. This is a measurement of half-inch thickness of Teflon in a coaxial sample holder. As you can see, we get the expected values for Teflon. Before any measurement can be made with the network analyzer, calibration must be performed. This is an attempt to eliminate the effects of systematic errors on the measurement. This is the model for doing error correction on a two-port network analyzer. It has two components, the forward model and the reverse model. Each of them have the various errors, systematic errors that occur when making a measurement, such as directivity, source match, load match, reflection tracking, transmission tracking. Each of these in both directions will affect the measurement. In order to do a correction, we have to determine all 12 of these error coefficients. Each actual S parameters, as you can see by the equations, is a function of the four measured S parameters. And as a note, the analyzer needs to make both the forward and a reverse sweep in order to update any one S parameter. To determine the 12 error coefficients, we measure some known devices, and by doing so, we can then calculate these error coefficients. Basically, most calibrations are performed either using physical devices such as opens, shorts, lows, and throughs, or more recently, you can use a electronic or an eCal in order to make the measurement. Here you make the connection to the end of the cables once, and the network analyzer will switch the eCal system to known states. Waveguide calibrations can be used using an eCal, but because of the simplicity of the calibration standards, it's much easier just to go ahead and do a TRL cal. In this case, we'll use a through, a short applied to both ports, and a quarter wavelength section of the waveguide. There are several possibilities for calibrating a free space system. One possibility would be using a TRM, or through, reflect, match calibration. And the problem here is it's hard to get a good broadband absorber over the entire frequency range. And because of that, this type of cal is seldom used in making free space measurement. A TRL calibration is also a possibility. The three standards here are through, measuring a metal plate between the two antennas, and then precisely moving one of the antennas to a known device. Now, the problem here is just the precision in which you can move that one antenna, and then after the calibration, replacing it back to its original position. Another possibility is to use a GRL calibration. It is a two-step process. Once you do a calibration at the end of the cables that you're going to use to connect to the antenna. The second step in the GRL calibration is to measure a through and a metal plate. Now, this system uses time domain gating in order to estimate the value of the directivity. So there's only, that's two less error coefficients that need to be determined. By doing this, we set the reference of the measurement at the surface of the metal plates. The gated response isolation calibration is performed by measuring the line, an empty fixture, and a reflect, the measurement of a metal plate inserted between the antennas. This is much like the normal response isolation cal. The only difference being is that all the measurements are made with the gating applied and around the position of the metal plate. Below is the hardware configuration for making a waveguide sample holder measurement. As you can see, the network analyzer is connected to some waveguide to coax adapters. Waveguide section is in between the two. As mentioned, before we can make a measurement, we need to do a calibration. Shown here are the devices we need to do the calibration. We can do a through by connecting the two waveguide to coax adapters together. We can do a reflect by placing the metal plate between the two. And then we can use the quarter wavelength section of waveguide to do the third standard of the calibration. Once a calibration is performed, we can make a measurement on a sample. The sample shown here is a piece of waveguide machined such that it will fit into the quarter wavelength waveguide section. This illustrates the calibration. Going from left to right, we have a measurement of the through, a measurement of the quarter wavelength line section, and finally the measurement of the reflect standard. In order to do the measurement, I'm going to use a application written in Excel using Visual Basic for applications to control the network analyzer to do the calculations and display the results afterwards. As you can see, we can set up the start and stop frequencies, the number of points, which model we want to use, and then some sample holder information, the length of the sample holder thickness or the sample thickness, the distance to the sample, and the sample holder type. In this case, it's waveguide, and we've put down the cutoff frequency for this X-band measurement. When the measurement is triggered, the measurement is made, the calculation is performed using the selected model, and the results are displayed. One thing that should be noted in the table, we see that the magnetic properties are close, not exact, but close to 1 plus J0. So this gives us an idea that, gee, this must be a non-magnetic material. So maybe we would be better off using a different model. If we use a polynomial model, selecting that the model is non-magnetic, we get other results. And as we can see, they're pretty much what might be expected for a piece of Teflon. Doing a similar measurement using a coaxial sample holder would be much the same process. We need to do the calibration and then make the measurement and do the number crunching in order to get the material measurement properties. They would not be repeated here. Here is a simple setup for making measurements on a piece of material. The sample holder is this frame, and there's two X-band antennas. And right here in the opening is where we would place the sample. We'd also place the metal plate during calibration at this position. The two blue sections of tape are just used for positioning purposes. To do a GRL calibration on this fixture, we're going to do a calibration at the end of the coax that are used to connect to the antennas. We'll do a TRL calibration here. After that is performed, we'll do the GRL calibration by measuring the empty fixture and the fixture with the plate of metal placed between the antennas. Here we use the same software that was mentioned or used earlier to define the measurement. And once we have done this, we can trigger the measurement and get the results. Here are the results after the measurement has been triggered and the calculation is performed using the Nicholson-Ross model. As you can see, it indicates that essentially this piece of material must be non-magnetic, and maybe we should use a different model as opposed to the Nicholson-Ross magnetic model. Here we calculate the same measurement using the polynomial model, and we're assuming here in the polynomial model that possibly it may be magnetic. And as you can see, we get essentially the same values that we had gotten before, but the magnetic materials essentially is 1 plus J0, probably is not magnetic material. When considering using the transmission line technique to measure the electromagnetic properties of materials, there's probably several things you need to consider. You can use this technique from somewhere in the 100 megahertz range up to about 1 terahertz. Obviously, the type of sample holder you're going to use will determine what frequencies you can make the measurements. At the low end, you can use coax from about 100 megahertz to about 20 gigahertz. Waveguide 1 gigahertz to 40 gigahertz. And the real reason for some of these limitations is the problem in machining the sample to fit in either a coax or a waveguide section. At much higher frequencies, the machining or the samples become very small. At lower frequencies, they begin to get larger in diameter. It might be not very useful. Free space, once you get above make these measurements from about 2 gigahertz up to about 1 terahertz. Once you've decided, you need to determine what am I really looking for. If you're looking for measuring a low loss materials, circuit board materials or something, if you're interested in getting a good gauge on the loss factor or the loss tangent, you might want to consider using one of the resonant cavity techniques, which wasn't covered here. The disadvantage to that is typically resonant cavity measurements are made at single frequencies. So that's kind of the trade-off between the transmission line technique and the resonant cavity technique. If you know your material is non-magnetic, you probably should use one of the non-magnetic models, such as the NIST model or the polynomial model. As a matter of fact, the polynomial model can also be used as a non-magnetic material by just assuming that the magnetic properties are equal to 1. Likewise, Nicholson-Ross calculates the magnetic properties first and then uses it to calculate the electric properties. If you set the magnetic properties equal to 1, then Nicholson-Ross can be used as a non-magnetic model. Here's a partial list of references. These include references to transmission line techniques and also some of the other techniques that we did not discuss. To stay current on material measurements research, you may want to go to IEEE Explore and search for that type of material. This is the end, or this concludes this presentation.